All right, well, everybody, welcome to the third day of the math sessions today. Today, we're going to be covering hydraulics. So today, we're going to be kind of starting where we left off yesterday with talking about flow rates and so on and so forth. Those will be very important. We will see those after we get through the static pressure hydraulics part. When we move into talking about the continuity equation, I mean, those of you who printed this off go, man, this is probably not as thick as yesterday's session or the session before. And that's because hydraulics is a pretty involved session as far as that goes. And what I mean by pretty involved is just to make sure that you understand the continuity equation is actually where we're going to start kind of putting together everything we've done with unit conversions and a little bit of algebraic manipulation, so to speak. I know, right? Everyone here's algebra, but I'm going to do my best to take the algebra out of this today for you, okay? And we will all see that. So we will be getting into static pressure hydraulics, flow pressure hydraulics with the continuity equation, and dealing a little bit with gradient slope in dealing with some density or specific gravity type information too. All right, with that being said, I think we can go ahead and have Matt launch the first poll, and then we'll get underway with stuff.
All right, thanks, Scott. Yeah, we're gonna start the polls off with the same one that you guys started off with every day. So this first poll, how many people are viewing this webinar at your location? So if you can take a moment to answer that, the poll should just pop up right on your main screen. Make sure that Zoom is your active window. If it's your active window, then you will see Scott's title slide of his handout. And we're up to about 90%. So just a few of you left to vote on this. So I will be compiling these when we wrap this course up and preparing a participant roster to send off to the drinking water operator certification program. They'll actually do data entry with this information. And then I will also be sending a copy over to the wastewater operator certification, and they will maintain that for their records. So if you're a wastewater operator, you just note that you have taken this course and they can pull up their report and verify your name is on it, and you should be all set to get CECs in that regard. 96%, so only two people that were missing on the poll question here, and we've been open for a little over a minute, so I'm thinking we can close this and turn it back to you, Scott.
Let's go ahead and get underway with things. All right, so the very first thing we're going to be talking about is basic hydraulics, or what hydraulics is. Hydraulics is the study of liquids, both at rest and in motion. Well, I know most of you are probably thinking hydraulics. You think of like the boom arm on a backhoe or an excavator, right? You're thinking about that ram that moves back and forth in order to curl the bucket and dig the dirt and so on and so forth. And the thing about that is, you know just as well as I do, if that's what you're thinking about, that it's hydraulic fluid being pumped through hoses and different valves that give that pressure in order to curl and move and extend and retract as it does so. So that is a hydraulics, and it's actually the study, and it's based on the motion of the liquid within the system itself. So now if you take and think about how water moves around your system, water moves about the system, so it's at motion, and then sometimes it's at rest if like it's in a storage tank or something along those lines, right? So hydraulics is the study of liquids, including water, because it moves throughout your system, which is supposed to be an enclosed system. So water treatment and distribution operators deal with this, right? We see it in plants, we see it in the water systems themselves. We see it in our daily jobs every day for all of us who are in the water industry. So that's what we need to know about hydraulics. We will be dealing with static today, and which is at rest, and then we'll be dealing with the continuity I might have spelled that wrong. The continuity equation, which is, I think I spelled it right. The continuity, which is in that motion, okay? We'll be dealing with different mains and being able to calculate the flow rates and velocities based on the equation. So with that being said, we have weight here, okay? So weight is based on the force of gravity, okay? And there's a lot that you can garner from it. You can talk about the acceleration of gravity, which is right here and blah, 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 right? But this isn't a physics lesson, so I'm not going to be talking about that. But one thing that is important to note, that gravity acts upon water, right? Now, if we were to put a stack of boxes, right? And we were to think about this, what I want to do is I kind of want to ask you, what stack of boxes is going to fall over easier? Is it going to be the short stack of boxes or the tall stack of boxes? Well, most of you are probably going to be like, well, yeah, as we stack boxes up, they get wobbly. Well, if it was a solid column, do we all agree that it's easier to tip over the taller boxes? Absolutely it is. And the reason is that the taller an object is, you can see that gravity has a longer reaction time on it just based on that, right? Gravity acts upon things that are taller versus things that are less, right? Maybe we've all heard the terminology, a low center of gravity, right? So the taller an object is, the taller the center of gravity is, which means the more gravity acts upon it as it pulls it down towards the ground. So the same is true for water, all right? Well, how does that relate to what we're talking about? Well, in the next couple pages, you'll understand when we get there, okay? But I just want you to know, right, that we know that taller objects, taller equals more gravity, right? That's something that we need to understand, though. Taller equals more gravity versus something that's shorter, all right? So we'll leave that conversation for now and talk about it in just the next slide here. So here on the next page, we have a thing called specific gravity, okay? And the thing about specific gravity is it's comparing the density of water. Well, what is the density of water? So we've kind of talked about it a little bit, but not really. So first off, we measure density by measuring mass over volume, okay? And you see I'm drawing a cube here and you're probably wondering why. Oh, it's going to be a teaching tool, I promise. All right. So density equals mass divided by volume, okay? And by mass, we're not talking grams or kilograms or anything like that, right? That you would think most scientists talk about, but we're talking about pounds, right? We're talking about pounds. And then we want to know a volume. Well, the volume that we typically use is cubic feet, okay? So yesterday we had learned that 1 cubic foot equals 7.48 gallons, correct? We learned this 2 days ago, technically, and we learned that 1 gallon equals 8.34 pounds. So if I had a cube and it was completely full of water, how much would it weigh? Well, because it's a mass divided by volume. So if I knew the mass in this, it would give me a mass per volume. So we learned, and you can see on your math formula sheet that there's a 62.4 pounds per cubic foot. Well, the thing about it is that's actually a rounded number. It's okay if you use 62.4, but it's 62.38 is its technical. But for this intensive purposes, for the fact that it's on your unit conversion sheet, we'll just say 62.4 pounds per cubic foot. Do you see how it's a mass divided by a volume? Mass, volume, cubic foot. So each cube of water that is 1 cubic foot in each direction weighs 62.4 pounds, right? So length, width, and height, they're all, they're 1 foot, not 1 cubic, my bad. Like that. So it gives you 1 cubic foot. So specific gravity is comparing the density of substance divided by the density of water. Well, why would we do that? The thing about specific gravity is, density of water. The density of water. So specific gravity, what it can do is it can tell us what things will do or how they react with water, and not react as in like a chemical going boom, not that kind of react. It allows us to understand how things in water might sink or float in water specifically, okay? So we're going to be talking about the very first substance here, is mercury. So if we were to take this cube and fill it full of mercury, that cube is going to weigh 849 pounds, okay? So 849 pounds is how much that thing would mercury weigh. Maybe some of you recall holding mercury in your hand as a kid. I'm 34, so I suppose, younger than some and maybe older than others on this call. But I've held mercury, believe it or not. I'm from a backwoods school up north. And no, I did not hold mercury straight on my hand like some of you may have. I held mercury in my hands via I have a glove on my hand and it was in a beaker, so to speak. So it wasn't directly on my hands, but I recall in ninth grade holding that it was like ridiculously heavy. And you can see that 849 pounds, that's a ton compared to water. But anyway, so for the fact that the density is cubic feet pounds per cubic foot, what we're doing here is we have 849 pounds per cubic foot divided by 62.4 pounds per cubic foot. We have learned what happens when you have units that are similar. They cancel, right? So first off, this has no units. It's very important to note that specific gravity has no units, okay? And when we do this, we get 13.6. And so there's something else to note. We talked about, or I had said, the reason we compare this to water is to kind of see how it would react with water, meaning will it float or sink? And oil, okay, that's something everyone goes to first. It goes, well, oil floats on water. It floats on water for different reasons, though, because typically oil is heavier than water. It floats on water because of being hydrophobic. It's a kind of afraid of water. You can think of it that way. So that's why it floats on it. So if we divide it and we get a number that is greater than 1, it will sink. So what do you think happens with mercury when we put it in water? That thing goes right to the bottom like a sinker. It's gone. And if the number is less than 1, what do you think it will? Well, if it sinks, if it's greater than 1, it's got to float. So if it's less than 1, it floats. And if the number is greater than 1, it will sink in water, okay? That's really what I have to talk to you about specific gravity, is understanding what the formula is for it. It's the density of an object divided by the density of water, which is 62.4. That won't ever change, okay? And knowing that it has no units and that things can float or sink based on what you get for an answer, okay? All right, elevation. So elevation is going to be very important with what we're about to talk about and we're about to do, all right? And what do I mean by that? So elevation is based on not feet above sea level, okay? Because I know like here in Lansing, what was it? At the dye water plant here in Lansing, it was 831 feet above sea level, okay? So would we ever look at, if let's say we have a water tower here, and am I ever going to look at the top of the water tower and go, that thing is, if I'm 831 here, we'll just say 986 feet above sea level. Would we ever say that? Well, that water tower is 986 feet above sea level, and where I'm standing at, it's 831. No, of course we're not. We're not ever going to say that. So elevation, especially in terms of static pressure hydraulics, is not going to be thinking about sea level. But what we're going to be doing is we want to know how high a water tower is. And the water tower here, we're just going to say is 135 feet tall. So it's 135 feet of elevation, and that's based on the ground being 0 feet, okay? So the reason that this is important is because it gives us a reference point. So the reference point for feet above will be the ground is 0, and feet above that counts as our elevation from there, if that makes sense, okay? Because thinking above sea level, it varies depending where you are in Michigan, right? And that's not what we want to do. So elevation, it's ground is 0 feet. Anything above that is positive elevation, okay? So why is that important? Well, the understanding that, okay. So before we get to all that, real quick, I'm going to draw a couple tanks here. All right, so I have a pressure gauge here and a pressure gauge here, and this is 1 million gallons, and this is 1,000 gallons. Okay, so my question to everybody here, I want to think about this. Both these tanks are 100% full, okay? So they're 100% full. One is 1,000 gallons, one is 1,000,000 gallons. Going to read the pressure gauge here at the bottom, okay? Pressure gauge here at the bottom, which one has a higher pressure is my question to all of you. Is it the 1,000,000 gallon tank has higher pressure, or is it the 1,000 gallon tank has higher pressure is my question. And I want you to think about amongst yourselves or with the people around you or yourself real quick. You tell me which one has a higher thing. You don't have to tell me literally, but just think about it for a second. Well, man, part of me would say the 1,000,000 gallon tank it's got 1,000,000 gallons. Of course, it's going to have more pressure, correct? Or is that right? Well, it's actually the same, because would you agree that both of these are the same height? They look really close to the same height. Yeah, of course. So they're the same height. The 1,000,000 gallons does not have more pressure. Yes, the tank is bigger. Yes, there's more water there. But the thing about it is, if we think about it in the scale of a tank, is there only a column of water like this in that tank in height? And there's a bunch of them, kind of like that, from the bottom to the top of it. And my point is, what is pressure measured in? Pounds. Being that most of you are probably watching this on the laptop screen, that means it's going to be about equivalent to what I draw. This is obviously not scale because the thing's as tall as them. But if this was 1 inch, this, man, if I could write 1 inch and 1 inch, would you agree that pressure is measured pounds acting on that square inch? Pounds per square inch. Yeah, absolutely it is. So that's why it doesn't matter how much water you have, because it's only these little columns of water that it's measured in, okay? So we have a couple conversion factors here on the bottom. And here's a better picture of what pounds per square inch looks like, right? It might be a big thing, but we're only looking at 1 inch squared, and it's the whole column of water that exerts pressure. Okay, so if you care to know how the math works, this is how the math works to get your pressure conversion factors, but I don't think we necessarily care, right? I don't, so I don't worry about it. What's going on? Okay, Matt, Was there COVID in this room? Of course there was. Matt, I have to switch rooms, dude. So,
Okay, we will wait for you to transition.
all right.
Okay, well, Scott is changing rooms. Just want to remind everybody that if you were registered for this event, then you would have received a follow-up email. And in that email had session recording links for session 1 and session 2. And I also attached to the email the 4-session presentation handout. So you should have received all of those yesterday. And then if you are new this morning, I have dropped a copy of today's handout in the chat, and you should be able to click on that if you need to download that to your computer. So we're probably going to be in a little bit of a delay here while Scott finds another conference room to be able to continue this class. He's using a computer as well as a document camera. So he does have a little bit of equipment to move around. And if you have any questions or anything like that, you certainly can feel free and put those into the Q&A box, and we can address those when Scott gets back. So I would expect that Scott will be back here in 2 to 3 minutes. Thank you.
People will hear me. Yes, no.
Yeah, I can hear you. It's a little faint at the moment.
Hold on a second.
And we do see your document camera, and we do see your problem set currently up. All right. Here. Come back again.
Hold on, I'm trying to.
Yeah, I hear you now.
All right, my computer's trying to. Well, that's unfortunate, I guess, for me. I guess if I get COVID, that's cool. Yeah. Sorry about that, everyone. I just our building, obviously, the room I'd been sitting in for the past 2 days teaching you guys has been exposed to COVID, and I got DHHS rule says that they got to come in and clean it, and I guess I've been sitting in there for the last couple of days, so that gotta love it. Anyway, so I guess with all right, so I left off talking about where our conversion factors come from. Okay, so our conversion factors are going to come from a couple different places. All right, so one way of thinking about it is, if we go back to the cube of water, the easy way of doing it is the cube bottom here, right? Would we all agree that there's going to be a gridded pattern on the bottom of this thing? That if we did like 12, this way and 12 this way, you're going to have a column of water all the way to the top of this thing, kind of like here. And if 62.4 pounds per cubic foot, you divide that by the 144 inches, and that's where we get one of our conversion factors, okay? Which is 0.433 pounds per cubic foot. So our point, man, PSI, I'm nothing like throwing you off the groove. Sorry, guys. So one way of thinking about this too is kind of like this, right? This is what I usually do to look at this, is that this is a 1 foot tall cylinder. And we have another cylinder here that is got a gauge here. And this cylinder is 2.31 feet tall. So if we look at this 1 foot tall and it's full of water, the PSI gauge here is going to say 0.433 PSI. And the other one that's 2.31 feet will say 1 PSI at the bottom here on this gauge, okay? So these are conversion factors, all right, that we will be using for doing static pressure hydraulics, okay? So the taller the water is, the more pressure it's going to have. As you can see here, I mean, it's kind of 1 foot is only 0.433, 2.31 is 1 PSI, okay? So you do not have to know both of these. They will give you same answers. You get to pick which one you use. Hate to tell it to you all, but most of the time, as you guys being my students, you kind of learn by de facto, right? And by default, I use 1 PSI equals 2.31 feet of water, all right? So I'm going to be using 1 PSI equals 2.31 feet of water, or water head, which is head refers to height of water, okay? So with that being said, I have some sample problems here that we're going to do. I'm going to do one and I want you to do the other. Okay, so I'm going to do this one here. What would the pressure be at the base of an elevated storage tank that's 150 feet tall? So the elevated storage tank, right? I'm going to tell you with static pressure hydraulic questions, I mean, this one's pretty straightforward, but some of the ones and a lot of the ones that you're going to see are not as straightforward. And they're kind of a story, well, there'll be story problems, but they're kind of a story problem that you should draw out and depict, okay? So this thing's 150 foot and it's completely full of water. There's a pressure gauge here, and we want to know what the pressure would be. So everyone goes, well, what do I start with, right? Well, this is a unit conversion essentially. So I'm starting with 150 foot. Well, if feet are on top, where do feet have to be to cancel? Down here. So 2.31 feet, 1 PSI up top. Those are those factors that we were just looking at. That's what they are. They are conversion factors. So this is 150 divided by 2.31, which will give me, I'll get my calculator here. Give me 64.94 psi. Okay. So that's how you do a static pressure hydraulics. Okay. I'll give you guys, we'll say 2 minutes to go ahead and do this one, and then we will do it together, and then we'll move on. All right. All right. Yeah, it's been 3 minutes. Okay. What will the water level be in a storage tank if the tank uh, if the gauge at the base reads 16 psi? So I don't know what kind of tank we got here. So, we're just going to build a awesome tank like that. All right. So it's saying that down here, it says 16 psi. But what we don't know is, that's a really bad question mark, but we don't know how tall it is, right? That's what we're looking at. So I'm starting with 16 psi. It is over 1. So 1 psi up here on top. It's got to be on the bottom to cancel. 1 psi equals 2.31 feet. So the psi's cancel. 16 times 2.31. Oh, I can't even use a calculator now, guys. It's not going good. 36.96 feet. Okay. All right, here in the next part, friction loss and head loss. Okay. Or friction and head loss. So first off, so I need to explain this to you all, and this is how I have found, especially with being virtual, is the easiest way to do this. Okay. So I'm gonna say that we got a water tower here, here, and here. Okay. So this is 2-dimensional. This is the ground. This is a water tower at 1 mile, 5 miles, and 10 miles. Okay, so the water runs this way and this way, this way and this way, and then this way and this way, okay? So I want everyone sitting there, rub their hands together, right? Well, it's getting warm. Yeah, well, what's happening when it's getting warm, or why is it getting warm, right? Well, it's getting warm because of friction, right? You rub your hands together, you have friction. So that friction is energy. It's energy loss, but it creates heat, correct? So even though water is an object, kind of like, I guess, if I were to think my Gatorade here, right? If you think of this as a pipe, you see there's some Gatorade that I drink most of it, but there's some there. And the water, I mean, obviously you don't want it going like this in your water pipes, because if it's doing that, that's not good. That things go kaboom when that happens. But you see that my Gatorade or water would be in contact with the surface of the pipe, just like here, right? Well, as the water is moving across through the pipe, would you agree that it's continuously doing this, right? It's continuing to heat up. So water will never get to the point where it's going to boil due to friction, but in it is incurring friction as it moves through your water pipes, correct? Do we agree with that? I think so. Because water pipes are not what are called superconductors, which are frictionless. Water moves through the pipes just like you kind of move your hands together, right? But water will not heat up and boil, like I'm saying. So the thing about it is, these are water towers at 1 mile, 5 miles, and 10 miles. And, for all I care, they're 10,000 foot tall, 10K feet, right? They have no height limit. But my question to you, this is a water treatment plant. The water flows from left to right here and goes up the towers. There are no booster stations, meaning there is no other pumps in the system than other than the high service pumps here at the water treatment plant, okay? So my question is, at 1, 5, or 10 miles, where will the water be the highest? Like, remember, these water towers go forever. There are no booster stations and there is no backflow. So the water goes left to right. Where will the water be the highest? Would it be 1 mile, 5 miles, or 10 miles? Depending upon who you ask, you're going to get a different answer, right? So the thing about it is, it would be 1 mile, okay? The water would be up here, and at 5, somewhere like this, and at 10, something like this would be the water levels, okay? So the fact or the reason that the water is highest at the 1, there is no booster stations, right? So the water is not going to gain any extra energy. Well, here, the water's only been in contact with the pipe for 1 mile. So for the fact that it's only been in contact for 1 mile, that means it only has 1 mile of friction, right? Versus 5 or 10 miles of friction. So the energy that's given to water by a pump is known as head. And water can only go so high based on the energy it's given, okay? That's kind of why on the conversion factor, it said 1 foot of head equals 0.433 PSI. And that's because head refers to how high the water will go, right? This term is known as head of water. The water can only go so high, and it's based on the energy that it has. When water moves through a pipe, it's causing friction, and friction creates energy loss, right? Kind of like things just, the reason why my calculator doesn't just move on its own is because of friction, right? I got to push it. It requires energy. So as water moves through the pipe, the more energy it's going to lose the longer it's in the pipe. Does that make sense? At 10 miles, it's moved through it way more than 1 mile, so it has less energy. Well, that energy is the head loss. As it loses it, it loses head loss too. So friction loss and head loss are related. The more the water is in contact with the pipe, the more energy it loses, the less speed of head it has to go up. Okay? I hope that makes sense. Well, there's something in a pipe that resists motion or can assist in the loss of friction. So let's say that's my pipe. Have we ever dug up a pipe and it looks like this on the inside of it? You know, it's supposed to be an 8-inch pipe, but it's got all this stuff built into it. This stuff, first off, is known as man, I spell this wrong every time. This is an I, tuberculation. This is known as tuberculation, okay? Which is just build up on pipe walls. So our old cast iron pipe from 1930 in our water system is going to have all this sediment built up in here, the rust and the calcium and all this different stuff built up. And when that stuff builds up in a pipe, do you think this would flow if we say that pipe versus, this pipe? Which one's going to flow better? Well, this one has no buildup in it, right? So tuberculation in pipe like this that's old, which don't go, oh man, ours is the only water system in the state. Okay, every water system in the state has tuberculation in it. I would be willing to bet $1,000 says there's not a water system in the state that doesn't have some form of buildup in their pipes. Okay, at some point, I'm willing to bet that. All right. So it's not just you. So don't feel bad about your community because there's other cities that are in the same boat as you or other communities in the same boat. Okay. But my point is if it has buildup, it's going to have greater friction as the water moves through it, meaning it has increased friction loss, which means it will have increased head loss. Okay. So this buildup is also measured as a thing called C factor. C factor is the measure of interior smoothness. All right. So your old cast iron pipe that looks like this versus your new ductile iron that looks like that, there's going to be a different C factor for both of these, okay? So high C factor, like, we'll say 100. Most ductile iron nowadays is only about 130 mortar lined. Means smoother. And low C factor, somewhere around 40 is what, like old cast iron like that is. It's somewhere around 40, means rough. Okay. These are important things and terms to know when thinking about a distribution system and how things work. A low C factor means that it's really rough, and a high C factor means that it's a smoother type pipe. 130 is not the highest that it goes. The highest C factor that I've heard of is like 150, and that's like brand new PVC. Brand new PVC is somewhere around 150. Does PVC maintain a higher C factor more length of time versus duct iron? I would say yes, because typically stuff isn't going to build up and stick to a PVC pipe, all right? So now here on the next page, well, okay, has everyone got this written? I'll make sure I give you guys a minute to write that down. There's a lot of stuff written there. Tuberculation, this is a thing, some of you may have heard of a technique called pigging, where you either run like a sponge type thing through the water main to try to scrub it, or ice sometimes is used to push through. And that's in an effort to like scrub off the interior side of a pipe. Tuberculation is also a reason why communities flush typically twice a year, spring and fall. Flushing is an increased rate of flow coming out of hydrants. And a lot of times that can mix that up. I mean, I know you always get complaints, right? Who's going, yeah, yeah, I know what you're talking about. The couple times a year that you're doing flushing, you turn on the hydrant and let it rip, and you want to flush till it's clean, but at the same time, you're going to get complaints from customers. Oh, rust in my laundry, my shirts, my white shirts are yellow now, and so on and so forth, right? But it's maintenance that needs to be done because if we didn't do it, it would just continue to build up and get worse and worse. And tuberculation like this can harbor bacteria. All right. So a couple times a year, this is why we flush, is to try to break this up, dislodge it, and get it out of the mains. All right. So here on the next page, page 44, you're going to see this, 45, and page 46 real quick. You're going to see these two things, okay? I want you all to do these on your own. So I'll give you guys like 10 minutes to do these, and then we'll come back together and go over them, okay? PSIG means PSI, okay? It's not a trick. So you're going to need to work through these, use the conversion factors that we gave you, and solve these, and then we will come back together and go over these. So I'll give you guys 10 minutes to go ahead and do that. There, hold on. Put my mic back the way it's supposed to be. All right. So let's go ahead and go through these. And then after we are through these, we will go ahead and go on to, yeah, I apologize, everyone. Ingham County is among the top 13 top counties in Michigan right now with COVID and getting the emails on like a daily basis. So, you know, some of you are probably wondering, are we back in the office or not? I have been. I've been in the office for like the last 2 weeks straight, going through exam applications and stuff like that, and here instructing you guys. But obviously tomorrow I'm going to just stay home. I will teach from home tomorrow and do my work remotely tomorrow, given what happened. So, but anyway, so here we are starting with 32 feet. You know, is that, I mean, it looks clear on the screen. Readjust it here. There we go. Here you can see we're starting with 32 feet. So it's 32 feet of water. Well, how many PSI? PSI is G, it just means PSI gravity, based on gravity, which all this is. So if I have 32 feet of water, 32 feet is over 1, so that means feet have to be down here to cancel, which is 2.31 feet, and 1 PSI up here. So 32 divided by 2.31 feet. Let me get my calculator out. I'm using a little bit of a different calculator today. So just so you know, if you couldn't find the one that I recommended, this calculator is also non-programmable, and you're allowed to use this one on the exam too. As far as Texas Instruments go, it can be anything up to a TI 36, okay? So if you only manage to get your hands on something like that, as long as it's 36 and under, you're okay. You're good to go, okay? So this is 32 divided by 2.31. And this is 13.85 PSI. Okay. So just as a side note, yeah, I know I'll talk about that in a little bit. I was going to give you guys some more valuable information, but I will tell you valuable information when we get there after break, okay? What is the water level in the elevated tank in figure B here? So you can see it says I have 105 PSI. So I'm starting with 105 PSI. It is over 1. So if PSI is on top, where does PSI got to be to cancel? Well, PSI goes here. Well, I know 1 PSI. And then it equals 2.31 feet, so that goes up top, which is 242.55 feet. 242.55 feet. That's a pretty tall water tower. 142.55. That's a, you know, I don't know what the largest or tallest water tower is in the world, but I'm definitely going to look that up on break now because I'm curious. So, all right. So 242.55 feet. All right. Look at the two figures below and answer the following questions. Calculate the water pressure at the base of an elevated storage tank and a standpipe in figure A. So what I need to garner from this is I need two pressures, but I need to know how high they are in order to solve for them. So I have 140 feet here and 140 feet. Does the 50,000 gallons even matter? No, because it's not based on the amount of water, even though it's equal. It's based on the height of water. And since they're both 140 feet, if I solve for one of them, I'm going to solve for both. So I'm going to start with 140 feet. The feet are on the top, so where do they need to be to cancel? Down here. And 1 PSI up top. So 140 divided by feet cancel, divided by 2.31 equals, so I got 60.61, 60.61. Round to the second decimal place here, as you can see it. So I got, all right. Now here in this one, calculate the water pressure at the base of an elevated storage tank as shown in figure B, okay? So we're figure B here. We got 130 feet and 70 feet. So I have two different things here. So tank, and standpipe. All right. So I have 130 feet of water here. That's over 1. The feet are up top. They got to be on the bottom to cancel. That means 1 psi is up top. So it cancels out like this. 130 divided by the 2.31. Which equals 56.28 psi. All right, now the standpipe is 70 feet of water. All right, and that's going to be just like this. 2.31 below, 1 psi up top here. So I'm going to get 70 by 2.31. And that's going to give me 30.30. Okay. So real quick, let's talk about a couple things. Okay, so that's our 2 different pressures here. But one thing, the next question says, referring to the 2 figures, how does the shape of the tank relate to water pressure in a system? Is there any advantage to them? Well, would you say that there's any advantages to them? The main thing I want to point out here is look at how the water is held between the 2. Okay, first off. So here we have 140 feet at both of them, and they're both at 50,000 gallons, right? Well, here we have 25,000 gallons, and you can see that the water level went from like here to there. So pretty much cut it in half. And then here it dropped, from here to there, like 10 foot. Here it dropped 70 foot, there it dropped 10 foot. Well, what did that do? What's the, who cares? It dropped 10, it dropped 70. Well, look at the pressures. They were both 60.61 before they lost half their fill. They went down by half. This one only dropped like 4.33, I think, something like that, 4.33. And this one dropped in half, didn't it? It went to 30 psi. So elevated storage tanks do have an advantage, right? Elevated storage tanks maintain system pressure during drawdown. And it's plain to see. So elevated storage tanks are done that way for a reason. All the water is held at the very top with this little riser pipe going up. So all the water is way up high. So during drawdown, it maintains its pressure. So it keeps your pressure within your system high, okay? Well, why would we want to do that? A standpipe it's mainly for storage in compact areas, okay? There's an advantage to it. It doesn't give you a whole lot of pressure. It does when it's full, but if we draw it down, it's not, right? But look at the base of this versus in vertical height. It's the same at the bottom as it is all the way at the top. So if it's only 10 foot across, it's 10 foot up here. Whereas this thing might have a 50-foot base and then a bigger bowl even on it, the bigger the tank gets. Does everyone agree with that? So these take up a lot more room. Yeah, they're good for maintaining pressure in your system, but they take up a little bit of room. So you got to have room to do it. All right. So there's a couple things. Maximum residential PSI. I want to cover real quick before we leave. And then there's a minimum system pressure. So going into a customer's home, do you know what the maximum allowable PSI is? So at their service line going into their house. It used to be 100 PSI, but in like 2016, it changed to 80 PSI. Maximum residential PSI going into the home is only 80. Okay. So minimum system pressure. What is the minimum that's allowed to be in your water mains? It is 35 PSI. Normal. Not allowed to be under 35. And then fire emergency. So fire pumps hook up and start drawing water out. is not allowed to drop below 20 psi. Okay, so just a little heads up, maximum residential psi is 80. System pressure is 35 as a minimum. And if you're under fire emergency, there's a fire broke out, it's 20 psi. Okay, those are the minimum. All right, with that, let's go ahead and take a 10-minute break, and I will see everyone back here at 9:50 a.m. All right. All right. Well, it's 9:50. We should be getting back here. It's time for Matt to go ahead and run the second poll question if he can, and then we'll get into this.
Okay, I'll bring that up while you're getting ready, Scott. So this is a simple question here, yes or no? Did you attend session 1 and 2? So if you attended both of them, select yes. If you only attended one or did not attend any, then select no. And again, these poll questions are really just to gauge your engagement and participation in the webinar. There is no right or wrong answer as long as you answer the question if you are interested in CECs.
Wow. Just trying to look over what we got, and I got 211. We'll be close. Like I said, I apologize. Everyone will get their CECs, but I know 84% of you are taking this for content, like, for stuff to help you pass your exam. So it isn't about CECs more or less for a lot of you. It's, I need this to pass my test. Man, should have had you do a poll question. Is it okay to stay over a couple 10 minutes or something for people, or would you be interested in?
Yeah, and that's, I mean, those that are interested in staying will stay. I imagine you're not going to go too far over.
No, it won't be. I mean, it was like 5 minutes interrupted me. And as you guys have all seen, guys and girls, that I'm pretty on with my times. I mean, I have been doing this for a long time by now. So I have my timing down on stuff. Just when you get hit with a curveball like that, I mean, what can you do, right? So,
Well, you navigated through it pretty well, Scott. So I think we're all in good shape. So we're about 90% have completed the poll question. I am going to close it here in about 15 seconds. So if you are interested in CECs, please answer the poll. If you're having difficulty, please submit a question. And remember, the Zoom webinar screen must be your active screen in order to see the poll question. Once you answer it, it does go away. So, all right, Scott, I am going to close this, and we have 92% of our respondents have attended session 1 and 2.
oh, that's a Matt question, not me. Okay. All right. Well, with that being said, let's go ahead and get underway so that we can. I'm going to try my hardest to make it at 11 so that everyone can see everything. Okay. So I guess if we get to that point, Matt, maybe if I'm not done, we run the poll so those who are here for credit can get credit, and then those who want to stay for the 5 or 10 minutes it'll take me, they can stay. All right. We'll get that bridge when we get there. All right. Anyway, so this is another static pressure hydraulics question here. And this one's a little bit different. It's more of a story problem, okay? A 125-foot high elevated storage tank sits atop a 45-foot hill. The water level in the tank is 22 feet below the tank's top. In the hydrant at the base of the tank, there's a hydrant. What is the water pressure at the hydrant nozzle if the nozzle is 2 feet above the ground? Give your answer in both feet of head and PSI. All right, so I'm going to tell you, first off, these are the type of questions that you're going to see on your certification exams. You could see some that are just like a one-liner. It says, 140 foot tall storage tank is, 13 feet below its top. What's the pressure at the bottom, right? But this is like an all-encompassing one. Okay, so what I'm going to tell you, the best thing to do with this, as you see, let's add a diagram for this problem. What it is best to do is to draw it out. So I'm going to draw it out. So this is going to be my hill. The hill is 45 feet tall. And there's an elevated storage tank right here that's 125 foot. Okay, so this is 125 foot tall. All right. And there says there's a hydrant right here at the base of the tank. And the hydrant nozzle, which is right here, is 2 feet. And it also says that the water level tank is 22 feet below. So we'll just, somewhere like this. This 22 feet. Would you all agree with, after you read the question, that's what the 125-foot tank on a 45-foot hill. The water level is 22 feet below the top. And at the base of the tank, there's a hydrant with a nozzle that's 2 feet above the ground. And it wants to know what is the pressure right here at that nozzle right there, okay? So, first off, I want to talk about something. I want to show you a thing, and we'll go from there, right? So if we imagine this is the hill kind of looks like this, right? There's going to be a water pipe coming down, and then there's going to be a hydrant lead coming off, correct? Off a main going up. So the water is going to have to come down the water tower this way. But in order to go up to the hydrant, it's got to go this way. Would everyone agree with that? So for the fact that the water is going down here to a water main and then running over here and going up to a fire hydrant, there is some vertical drop there because there's extra height going down in the main, but then there's water coming back up from the main, right? So I'm going to tell you water main rise and fall is not included. All right. I do get that your systems are uneven. And what I mean by uneven, you might have a pipe over here in one street on Maple Street that's 3 foot deep. And over on Michigan Avenue, it's 8 foot deep, right? Maybe you're a small town, you don't even have a Maple, Michigan Avenue. But you get my point, is the fact that the distribution system may not be considered at the same depth, right? So yes, does that play a part in hydraulics? A little bit. But the thing about it is we can't go for the little bit, right? We have to go for the majority of the way things work. So for the fact that there's a rise and fall coming and going to a water main, we do not include that in our height calculations. We consider it negligible, okay? So any of the below ground action here from the water main between these two, we don't include that when talking about the height of water. But where we do look at water height is above ground here. So all the water in the tower, and then we measure it as it goes above the ground over here, okay? And I'll show you kind of a difference, right? If we imagine, let's think about our water tower now. Right here at the base of the water tower, what I'm wondering is how high is that water? At the base of the water tower, we don't care about the hydrant at the moment. Well, it's 125 foot tall and it's 22 feet below. So it's 125 minus 22. So at the base of the tank, it's 103 feet. Okay. So we're going to say that it's 103 feet here, correct? Well, water's got to go above ground over here. It's not coming down. As the water goes down, that's where you get your pressure. But as the water goes up, you lose pressure. Yeah, that's pressure. You lose pressure as you go above ground. So if it's 103 feet here, it hits here and then it goes above. How many feet does it go above? Well, it goes 2 feet here. It goes up 2 feet. So you have to subtract that 2 feet from your total head. So as the water comes down the water tower here, it comes to the ground level and then goes above. So our total feet of head is 101 feet. Because anytime it goes above ground, you have to subtract it. So anytime it goes back up, you have to subtract it from your height of water. So it's 101 feet. Well, if you have 101 feet, how do you determine the pressure? Well, just like before, 100 feet on top, feet down below to cancel, 1 psi. So that's going to give me 101 over 2.31. And it's going to give me 43.72 PSI. Feet cancel. Okay. This is how the questions are going to work on the test. You're going to see questions very similar to this, okay? So it's best to draw a diagram and think about it, okay? I do want you to know, like I pointed out here, anytime you come back above the ground, you have to subtract that height, okay? All right, so there is a hydrant at the base of the hill. What is the pressure in the hydrant nozzle if the nozzle is 2 feet above ground? So it's saying here at the base of this hill, there's a hydrant here, and this is 2 feet. But the water's got to come down this way and run all the way down the hill before going up the hydrant lead up that. Okay. So we have a thing here. What is the pressure at that nozzle? So I'm going to give you what you have to do. So the water here is 103, correct, at the bottom of the tank, but it goes down a 45-foot hill. Would we add that hill to the height of the water? Absolutely, you will. The part of the water main that we consider negligible, you see this part right here, going from the main up and from the main down here, that's the part we consider negligible. When you throw in a hill, well, you add that hill height, which is 103 plus the 45 of the foot of the hill, gives you 148. But then you go back above ground 2 feet here, so you have to subtract the 2 feet, and you get 146 feet of head. So we got to convert that to pressure. But one thing I want to point out here, this is common practice. Water towers are often built in the highest places of town, okay? And the reason for this is free height. It's free elevation that you don't have to pay for, okay? Towns will build water towers or storage tanks on top of the tallest point of hill or the tallest point of town if there's room on purpose, because it'll give you free elevation and free pressure that you didn't have to pay for, right? So imagine the hill's 100 foot tall. That gives you 100 extra feet of PSI to feed into your water system and to boost the pressure throughout it. Marquette does this. Jackson does this. It's very common practice to see it. Cadillac, Michigan does it. That one can be seen from the highway. If you're ever going up 131 past exit 176, start looking off to the left for a great big blue water tower. Theirs is one of those pedestal water towers where it's kind of like a big dome with multiple pedestals around it as it goes. You know what I mean? This is a big globe thing, and these are little things supporting it. So it's a really big storage tank, but that's on top of a hill there. Marquette has a big elevated storage tank on the tallest point of hill town because Marquette's really hilly, so it helps drive the water up those hills. All right, so 146 feet. The feet are up top. They have to be down below to cancel. And 1 PSI here. So this is 63.2 PSI. Do you see what the hill did? Hill gave you almost 20 PSI between the two. It's 43 to 63. All right. So the next thing we're going to be talking about is hydraulic gradient slope, right? So gradient means it's the rise over the run. So what I mean by that is the height difference between the two ends. In this case, it's 1 foot. And the run is 20 feet long. The rise over the run. So if you do the rise of 1 over the run of 20 feet, you're going to get a gradient slope of 5%. So this is used in water systems to determine if you have a different pressure on the other end versus the pressure here, right? Well, the pressure on this end is going to be lower than the pressure over here because it went down by foot. So it'll have more pressure over here. So this often comes into play with systems kind of like this. You know, here you go down a hill, there'd be a slope there, and you could figure out the height difference if you knew it, but you didn't know that, okay? And how would that work? Okay, so here is another part of that question we've done. 500 feet away from the hydrant at the base of the hill, the water main leading from that hydrant near the tank slopes downhill at 4% slope from the other hydrant. What is the pressure at the hydrant farthest from the tank? Okay, so I'm going to redraw this real quick just to make this real quick. Right. And there's a hydrant here. And then it says that this slopes away from that hydrant, right? And it's 500 feet. And then there's a hydrant here down that slope. We need to know what this height difference is, right? Because you know this is 45 feet. This is 125. This is 22 feet below here. This is what we know. But we only know that this is a 500-foot hill at a slope of gradient down 4%. So what we need to do is we need to figure out that rise. Well, all you do to figure out that rise, if you know the percent slope, you first off got to convert this to 4%. And then you go 0.04 times by 500. This will give you this right here. So if you know the slope difference, it will give you that. And I come out with 20 feet. Okay. So now we were at 148 right here, remember? We're at the base of that because we're at 103 plus 45 is 148, and then add the other 20. So 148 plus the 20 feet gives 168. Well, what happens when you go above ground? What do you need to do? Subtract 2, so we're at 166 feet. 166 feet up top, PSI on the bottom, or feet on the bottom, PSI up top, my bad. So the flow with that, or the pressure at that hydrant, it's gonna be pretty good. .86 PSI. All right, so that hydrant has got some good flow. If you need some good flow, you might be able to just break the cap off that hydrant, turn it on, it might just put the fire out for you, right? I'm just kidding. That's not true. It wouldn't work like that. All right. You know, I guess, did everyone get this written down? I don't think I went through it too fast, but I'll give you guys a minute real quick. All right, we should have that all written down. All right, so flow rates, filling capacities, and the continuity equation. So we're back to flow rates, okay? We're back to what we talked about yesterday a bit, and the day before, and the day before, right? We're only 2 days. So the last 2 days we've talked about this stuff, all right? So if you remember, we talked about flow rates. There's gallons per minute, million gallons per day, and then there's CFS, or cubic feet per second. And I told you that cubic feet per second is the standard unit, okay? And that flow rates are often referred to as the letter Q. So here in the very first example, we're going right back to what we know. Convert 825 gallons per minute to cubic feet per second. Here's the conversion factors right here. So if gallons are on top, where do they got to be to cancel? Right here, I see 7.48 gallons. Well, that equals 1 cubic foot, so that goes up top. Gallons cancel. Well, I see minutes on the bottom. So minutes need to be on the top. To cancel 1 minute equals 60 seconds. So we're going to get 825 divided by 448.8. And we're going to get 1.84 cubic feet per second. So I'm doing this as a reminder of how to do this, because if you are not given cubic feet per second, you must convert them, okay? Okay, so here on the bottom, we're going to find a multi-step, this page and next, there's going to be a multi-step example here and more questions adding upon themselves, okay? So find the volume of a ground storage tank that has the diameter of 45 feet and a height of 20 feet. Determine how many gallons this tank would completely hold. Well, if we remember, the volume formula for a cylinder is 0.785 times diameter times diameter times the height. This question is asking for gallons. How do we go from cubic feet to gallons? Does anyone remember? Well, you just multiply by 7.48. So this is what our equation is going to look like, right? So let's go ahead and insert the stuff we know. Diameter is 45 feet, so 45 times 45 times 20. And then I got to get it to gallons, so let's multiply it by 7.48. 0.785 times 237,809 or 800, oh boy, 7.9 gallons. 237,807.9 gallons, okay? So that's how many gallons the tank will hold. Well, if that tank from the previous example were to be filled at a rate of 550 gallons per minute, how many hours would it take? Okay, so there's a detention time formula on the back of the math formula sheet. Detention time, did I spell that D? I spelled detention time. And it equals volume over flow rate. Well, the thing about it is detention time and fill rate are pretty much the same thing. All right, so how long is it going to take to fill the tank? Well, you take the 237,807.9 and you divide it by the flow rate. There's a caveat to this, doing this though. These two units, the flow rate and the volume, must match. Meaning if one is gallon, the other has to be gallon. If one is cubic feet, the other has to be cubic feet. Does that make sense? It's an absolute must because you can't cancel your units properly and you'll get a wrong answer if the units don't match. This case, they both match. So the only thing it's going to leave you with is minutes. So if I do that, I'm just double checking, make sure I got the right answer here, 550. You're going to get 432.38 minutes. Okay. Now you divide that by 60 to get it to hours. and you will get the 7.21 hours. Okay. So page 49 and page 50 have some example problems on them. I want you all to take about 8 minutes to do page 49 and page 50, and then we'll go over them together, okay? So I'm going to give you guys 8 minutes to try these out. So 10:24, we'll come back together and do these, okay? All right, well, it's been 8 minutes. Okay, what is the volume of an of a tank? Elevated. It is 26 feet long, 15 feet wide, and 9 feet deep, and it asks for it in cubic feet. So my question first off is, what shape are we dealing with here? Are we dealing with a cylinder or a rectangular prism or box or whatever you want to call it? This has 1, 2, 3 measurements. So this is it is a box, right? The volume of that, if you recall, was 26 times 15 times 9. You just multiply them all together, make sure that they're all the same units. I'm not playing a trick question on you. So I got 3,510 cubic feet. So now, I should have drew that better. How many gallons will a tank hold if there's an overflow drain located 7 feet from the base of the tank? So what it's saying is so this is my tank. Originally it's 9 feet tall, right? But there's a drain here and a drain here and a drain there, a couple on the back wall, a couple on this wall. It's saying that these drains are 7 foot from the base. So if we're trying to fill it and there's a drain 7 foot above the ground, will you ever be able to fill it to 9 feet tall? Absolutely not, because the overflow drain is at 7 feet. So you want to know how many gallons a tank will hold. Well, first off, we have to redo our volume because it's based on 7 feet because there's an overflow drain there. And I want to know how many gallons it is, so I'm going to just times it by 7.48. And 26 times 15 times 7 times 7.48 is 20,420.4 gallons. So 20,420.4 gallons. All right, now the next question is, if the tank fills in 55 minutes, what will the flow rate be in gallons per minute? So if you're looking for a flow rate in gallons per minute, well, do you know how many minutes it was? It says 55. Do you know how many gallons it is? 20,420.4. So you just take the gallons with the minutes and you divide it, and that will give you gallons per minute of 371.28 gallons per minute. So if it's asking for a flow rate and you know the volume of the tank and the time, that will give you a flow rate. And it kind of lays it out for you with saying it's gallons per minute. So you write it out, the units, and you can see where each of the two things you have go. Just a little trick with flow rates like that, all right? An empty tank measures 75 feet long, 14 feet wide, 20 foot wide, 14 feet deep. If 122,200 gallons are pumped into the tank, how high will the water level rise in the tank? So first off, it's this shape, isn't it? We're going to dump water in there, and the water level is going to rise so much. That's what we don't. Do you remember how to do these? I showed you, I think yesterday we did this. Remember, we have the part of what you're going to put in the tank, but do you have the whole thing? So I have 122,200 gallons. How do I know how many gallons this tank will hold? Well, the volume for this is length times width times the depth. Well, I need to know how many gallons it is, so I'm going to times it by 7.48. 75 times 20 times 14 is going to give me 157,080. So that's the whole thing. Because remember, as you fill this, the only thing that changes is the height or the water level, right? It is not the length or width. Those wouldn't change, but the depth will change. So 122, 200 divided by 157,080 gives me 0.78% or 78%. So 78% of the tank is full, and that represents the height, because the only thing that ever changes is the height of the tank. So I need to times that by 14. So 0.78 times 14 will give me 10.92 feet. All right. Water flows from the above tank to another at a rate of 175 gallons per minute. The other tank has a height of 10 feet and a diameter of 25 feet. At what level will the water be in the second tank after the water flows into it for 2 hours? Well, how many, do I even know what the total gallons of water is I'm putting into this thing? No, I don't, but I can solve for it. So I want to show you a trick. So if you know the pumping rate, which is 175 gallons per minute, anytime you see a pumping rate and you see a certain amount of time, I recommend converting the hours to minutes. So it went for 120 minutes. And the reason for that is for the fact that you're 175 gallons per minute. So that means each minute there's 175 gallons going into wherever it's going, into this tank, right? So it does this for 120 minutes. This will give you your total gallons, okay? Whenever you see a pumping rate with a certain number of hours, convert the hours to minutes and just multiply the two. So this gives you 21,000 gallons. Well, that tank is something like this, right? So the volume for this is 0.785 because it's a cylinder times the diameter times the diameter times the height. Well, I'm going to need to know gallons because I need to know what percent of it is full. So multiply it by 7.48. Oh, this is 25, not 20. Gee, Pete. Times 10 times 7.48. It'll give you 36,098.75 gallon per minute. So now that I know that, can I figure out what percent full it is? Absolutely. 36,698.75. I get 0.57, so that's 57% full. And that's 57% of the height, which is 10 foot, so it's 5.7 feet. All right. A 425 gallon per minute pump fills a 375,000 gallon standpipe. How many hours does it take to fill the tank to the halfway point? So when reading questions, be very careful with things because the devil is in the details here. So I'm not filling the whole tank. I'm only filling it halfway, right? So if you remember, there was a formula for figuring out this volume divided by flow equals a time. Okay. Well, I first off need to figure out how many gallons I'm dealing with here. And I got to cut this in half, so I divide it by 2, which gives you 187,500 gallons. Well, I know the flow rate is 425 gallons per minute. That leaves me with 441.18 minutes. How do you get minutes to hours? You just divide by 60. and I get 7.35 hours. All right, if a tank holds 75,000 gallons and the flow into the tank is 275,000 gallons, how long will it take to fill? Well, this is like the one we just did above it here. 75,000 gallons, and it's 275 gallon per minute. It's going to cancel. And that's going to give me 272.73 minutes. This doesn't ask for hours, so you can leave it as minutes, but I bet money some of you did this, so I will just do it anyway. Show you that it is 4.55 hours. All right. Now we're going to move into the continuity equation, okay? So the continuity equation is flow hydraulics. You can determine the flow rate of water within a pipe by knowing the velocity and the diameter of a pipe. Or you can determine the velocity if you know the flow rate and the pipe diameter, okay? So the continuity equation is Q equals V times A, okay? Or QVA. Some of you have maybe heard of it referred to as that, as a QVA question. And QVA questions have a couple of unique things about them first. And the first thing is the equation itself. Q, flow rate, equals velocity times area, okay? So everyone goes, oh boy, here we go. This thing's awful and horrible and everything else about it. So the Q is cubic feet per second. The area and everything we've done so far has been what? Square feet. We've determined a square feet. And now velocity is not volume. The V here is velocity. And it stands for feet per second. Okay. So first off, if we give you a continuity equation, you have to have two of the three things in order to determine the other, okay? You got to have two of three. That's how it works. And the other thing about it is you look at that and go, oh man, if I needed two of the three, that means algebra, doesn't it? It does. It does mean algebra. But a lot of people go, oh, I'm done. Algebra, I'm done. Not doing it. Well, I'm going to introduce you to a thing that I like to call the continuity triangle, where it is Q over VA. And again, remember the area units are square feet. This is cubic feet per second. And this is feet per second. And this is also velocity, not volume, okay? So if you have two of the three things, you can solve for the other. And this triangle kind of makes it self-explanatory. If it's above and below, what do you think you do? You divide, right? But if it's across from each other, what do you think you do? You multiply, okay? Q, if you have flow rate and area, you can solve for velocity or vice versa by dividing. But if you have velocity and area, you multiply and solve for the Q or the flow rate, okay? So you got to have two of the three things. Units for the continuity equation must be as shown above in order to do them properly, okay? All right, so this is a QVA or the continuity triangle. And how does it work, okay? The units must match. That is the biggest importantest, most importantest thing. Importantness isn't even a word, but I made it up. It's a good word. The most important thing is to make sure that the units match, okay? Well, how do I know I'm going to be doing a continuity equation by reading it, right? It's like one of the biggest questions I always get asked. How do I know it's continuity? And I'm going to tell you, you can figure out its continuity by one word. Velocity. The only time you're ever going to see velocity mentioned is in a continuity question, okay? Does that make sense? If we're reading questions and we see the word velocity, it's an indication that that's a continuity question, okay? So what is the velocity of water in a 12-inch main that is a flow rate of 3 million gallons per day? Well, crap. And remember, this is that 3 million gallons like that because you don't see all the zeros behind it. That's how you know it's that unit, okay? So if I think about my continuity triangle here in reference to this question, I have to have two things. 12-inch main. Can I get the area with a 12-inch main? Yes, you can. And the question was nice enough to tell us we have our Q, but there's a problem with it. First off, it's million gallon per day. So I got to get rid of this by multiplying by a million. Now I'm going to have 3 million gallon. Oh boy, I didn't do enough zeros. And I need to get it to cubic feet per second. Well, let's see. 7.48 gallons. If gallons are on top, they got to be on bottom. Look at, I'm at cubic feet. I'm getting there already. But now I got to get days to hours. So if days are on bottom, where do they got to go to cancel? Right here. 24 hours. Well, I got to get hours to cancel. So hours are on bottom. Days, cancel, gallons. If hours are on bottom, they got to go up top. Well, what does 1 hour equal? 60 minutes. Well, minutes are on the bottom. So where do they have to go to cancel? Minutes, minute, 60 seconds. So now I'm going to go through, multiply by 646,272. This is actually wrong. That's what I thought. This is 4.64. So my Q is 4.64. So now I'm going to draw my triangle down here. Q, B, and A. My A, oh, I didn't find my area yet. This is 4.64. Now I need to find my area. It's a 12-inch main, so you got to divide 12-inch by 12 to get its feet. The area equals 0.785 because it's a circle times 1 equals 0.785 square feet. So here we go, 0.785 goes here. I don't know my velocity. Can I solve for it though? 4.64 over 0.785. So it's going to be 4.64 divided by 0.785, right? Which is going to give you a number of 5.91 feet per second. Okay, so that's how the continuity triangle works. You got to see what you got, and then you got to do the rest of them, okay? So here on the back are 4 more questions. I'm going to give you all 7 minutes to do these. We will go over them together, and then we will hopefully finish right at 11. I'm going to try my best to finish right then, okay? So 7 minutes. We'll meet back up at 10:50 sharp after you've tried these a few of them, okay? All right, it has been 7 minutes. In should be a not in, but anyway, a 10-inch water main is flowing at a velocity of 2.5 feet per second. What is the flow rate of the pipe in cubic feet per second in gallons per minute? Okay, so remember with the QVA, so I'm going to put it over here. With QVA, we have VA and Q in our triangle, and you got to have two of the three things. A 10-inch water main has a velocity of, so first off, velocity indicates it's QVA question, and I know the velocity, so I'm going to just go ahead and put that there in my equation, 2.5. The other thing I do know, though, is my area. I just got to solve for it, don't I? So the first thing here to do to a 10 inch is to divide it by 12. So the area for a circle is 0.785 times, well, 10 divided by 12 is 0.83 times by 0.83. So we need it in, remember, everything, except for those of you taking an S1 or 2, all inches convert to feet, all right? So then what we need to do is when we multiply this together, we're going to get 0.54 square feet. So 0.54 is going to go right here. Now to solve for Q, we just need to multiply the two. 2.5 times 0.54 is going to give me 1.35 cubic feet. So 1.35 cubic feet per second. Now it wants to know gallons per minute. So cubic feet per second to gallons per minute. That is a conversion, all right? So if 1 cubic foot equals 7.48 gallons, cubic feet are on top, got to be on the bottom to cancel. Gallons goes up there. All right. If 1 second's on the bottom, where does it got to go to cancel? Well, here, I need to get it to minutes. So this would be 1 minute, 60 seconds. So when I do that, I get 605.88 gallons per minute. All right. Now, if the same main is flowing at 1.0 feet per second, what would the flow rate be? So again, VAQ. It said 1 feet per second, so that is my velocity. If the same main, well, if it's the same main, what's my area then? 0.54. So the flow rate is 0.54 cubic feet per second. 0.54 cubic feet per 1 second. It's kind of like up here, isn't it? Yeah, you're going to do the same exact thing. Cubic feet are on top, 1 cubic foot below to cancel, 7.48 gallons. And there's 60 seconds, 1 minute. Oh, not cancel gallons, cancel this. So that's going to be 0.54 times the 448.8. And that's going to get me 242.35 gallons per minute. All right. The same question that's been there for a while. Yeah. All right. A 1,000-foot section of new 16-inch water main is being flushed at a velocity of 3.2 feet per second. What flow in gallons per minute will be required to do this? So my first question to you is, what type of question is this? I know it's kind of a dead giveaway. We're in the continuity equation section, so that's what I would hope it is, right? But the word velocity here indicates that it is continuity. So let's do our continuity triangle here. B, A, and Q up here. All right, so my velocity, I already know, is 3.2. So I'm going to go ahead and write that in there. A 1,000-foot inch of 16-inch water main. Well, it says it's 16-inch diameter, so I can use that to determine my flow rate, right? Or my area. First thing is divided by 12. Area equals 0.785 times by, well, 12 divided by 16 is 1.33 feet. Do I need 1,000 foot? I do not, because 1,000 foot would be used for volume. V here stands for velocity, not volume, and we already know it. It's 3.2. All right, so I got to figure out my area here. And this comes to 1.39 square feet. So 1.39 there. So how would I get my Q? I got 3.2 and 1.39 there. Well, I got 4.45. 4.45 cubic feet per 1 second, because it wants it in gallons per minute. So what do I need to do? The same as these conversions right here, all right? 1 cubic feet on the bottom, since it's up top, it cancels. 7.48 gallons here. And if seconds are on the bottom, they need to be up top to cancel. So 60, 1 minute. So they cancel like that. This gives me 1,900. 1,997.16 gallon per minute. All right, we got one last question and then we are done. Okay, so number 4 is it's not as hard as you made it out to be, maybe. Okay, so solve for the velocity given the diagram here. Okay, so the first off is I have a diameter, I have a velocity. So this is a QVA question. The V I already know is 0.8. Area I don't know, but I can solve for it, correct? So what you need to do is you need to ignore that. And I guess I could use my phone. Let's just ignore that part of the equation for now, okay? Can I solve for my area given I have 18-inch? Well, absolutely. I got to just do 18 divided by 12 first off. So 1.5 feet, okay? The area equals 0.785 times by 1.5 times by 1.5. Do we all agree with that? Because that'll give me my area, 0.75 times. I get 1.77. So what would my flow rate be for this side? How would I determine it? 0.8 times 1.77, right? I get a flow rate of 1.42. Okay, so over here on this side of the pipe, we have a flow rate of 1.42 cubic feet per minute, or cubic feet per second, not minute. 1.42 cubic feet per second. Okay, so this water, the 1.42 on this side, is all going in here. So we have a flow rate of 1.42 cubic feet per second going into that, what is a 10-inch over here, right? Does the water just disappear? Can this 10-inch carry the same amount of water as this 18-inch? Well, logic goes, well, no, I can't. It absolutely can't. But does the water just disappear then? Does it just exit the pipe and blow out? No, of course it doesn't, right? Well, how silly would that be? Water doesn't just leave the pipe. It doesn't do this. It stays in the pipe. So you can see that all the arrows converged here. So that means that the flow rate here, or Q1, is going to equal the flow rate over here, Q2. The flow rate stays the same, okay? So flow rate remains the same. It doesn't just disappear. Okay, well, knowing that then, VA, I don't know velocity, but I'm working on. And I know my Q. This is 1.42. Well, I can get my area, divide this by 12, and it's going to give me 0.785 times 0.83 times 0.83, which will give me 0.54 square feet. So 0.54 here. So 1.42 divided by 0.54 gives me a velocity of 2.63 feet per second. So if you look at the velocity, what happened to it? Well, it increased. So going from a large to small main, velocity will what? It will increase, obviously. The water is being squeezed down, so it's got to go faster to get the same amount of water in there. Now, small to large would be opposite. Velocity will decrease with this, okay? And that's how you do those, just like that. The flow rate stays the same in both, and it will increase in velocity. And it's obvious, you can see that 8 inches made that velocity increase by 3.5 times almost from this. So velocity will increase as you go from large to small. If you go from small to large, it will decrease. All right. With that being said, I thank you all for staying, the couple minutes late. Matt, if you can you go ahead and put up the poll question so that we can be done with today?
Yes, sir.
I apologize for the whole I got to move and all that stuff, and because we would have been done 10 minutes ago at this point, but I promise tomorrow I will not, I will be staying home so that I don't get interrupted by people like that.
So we've got the poll question up there, and you've had 3 days of sessions with Scott. So we're curious, would you recommend this course in a virtual format? And really, it's a reflection on Scott's ability to convey this in understandable methods. So, and if you are voting no, we do have this class coming up in Detroit in person. So if that's of interest to you, you can find more information on that at our Eagle Events website. So we're up to about 95%, 100% voting. This is the first poll that we have. And so it looks like we've dropped a few participants.
Yeah, we lost a couple, yeah.
I'm going to go ahead and end the poll since it's at 100. And Scott, 46 out of 48 of those that responded say yes. 96% recommend this format. So I think it's a reflection on your ability to convey some of these difficult topics into understandable terminology.
I might have got that extra if I wouldn't have had to move rooms today, you know what I'm
saying? Maybe.
All right. Well, thank you everyone for joining me. Enjoy the cool weather today, especially if you got to work outside. I am definitely later today going to be enjoying it myself. Fall is among us, so get ready to start seeing some colors in the next couple weeks. Starting to show up. All right.
And we will be following up with you in the next day or so with a copy of the recording for this session. So look for an additional communication from us. Thank you and have a great day.